September 26, 1918, the Meuse-Argonne Forest, France, a lone American M917 tank, a license-built copy of the French Renault FT, lurches across the cratered landscape. Inside, the commander, a young lieutenant from Ohio, peers through the vision slit. His world is a claustrophobic symphony of roaring engine, clattering tracks, and the percussive drumming of German machine, gunfire against his thin steel hide. The armor on his tank is a mere 16 millimeters at its thickest, designed to stop rifle bullets and shrapnel, nothing more. Suddenly, a deafening crack echoes through the tiny compartment, and the world turns white, hot. A German 77 mm field gun has found its mark. The shell, a marvel of German metallurgical science, punches through the American-made plate as if it were cheese. The M1917 and its crew are instantly immolated. This was the brutal reality for American forces in the Great War. They were fighting a 20th century war with 19th century industrial capacity, particularly in one critical area, hardened steel. While American industry could produce millions of tons of steel, it couldn't produce the kind that mattered most on the battlefield, armor plate capable of defeating modern artillery. This is the documented story of how one American company, Bethlehem Steel, led by a visionary industrialist, solved this impossible problem and forged the armor that would not only protect a generation of soldiers and sailors, but also lay the foundation for America's rise as a global military power. In 1914, as the great powers of Europe plunged into a war of unprecedented industrial ferocity, the United States remained a nation blissfully unprepared for the horrors to come. America was an industrial giant, but a lopsided one. It could churn out rails, bridges, and skyscrapers, but it lacked the specialized industrial capacity for modern warfare. The most glaring deficiency was in the production of high-quality, hardened armor plate. At the turn of the 20th century, the global standard for armor was set by Germany's Krupp and Britain's Vickers. They had perfected the complex processes of carburizing, hardening, and tempering steel to create armor that could withstand the ever-increasing power of naval guns. America, protected by two vast oceans, had allowed its own armor-making capabilities to atrophy. In 1916, the United States Navy, awakening to the growing threat of a world at war, could source armor plate from only 3 companies. The total annual output of these firms was a mere 25,000 tons, barely enough to build a single battleship. The Navy's ambitious shipbuilding program, authorized by the Naval Act of 1916, called for the construction of 10 battleships and 6 battlecruisers, requiring hundreds of thousands of tons of armor. The existing industrial base couldn't meet even a fraction of this demand. Without a radical expansion of its armor-making capacity, the United States would be unable to build a fleet capable of defending its interests. The consequences of this failure were stark. An unarmored or poorly armored fleet would be sent to the bottom of the sea by the superior guns and shells of the German high seas fleet. On land, the situation was even more dire. The United States Army had no modern tanks and no domestic capacity to produce the armor plate required to build them. American soldiers would be sent into the meat grinder of the Western Front without the armored protection their British and French allies took for granted. The nation's industrial might, the very thing that was supposed to be its greatest asset, was facing a critical vulnerability. The problem wasn't a lack of steel. It was a lack of the right kind of steel and the knowledge and equipment to produce it on a massive scale. The man who would solve America's armor crisis was not a naval strategist or a government bureaucrat, but a classic American industrialist, a risk-taker with a flair for the dramatic and an almost fanatical belief in the power of technology. His name was Charles M. Schwab. Born in 1862 in Williamsburg, Pennsylvania, Schwab was the son of a woolen mill worker. He began his career as an engineer's helper in Andrew Carnegie's steel mills, driving stakes for a survey crew for $1 a day. But Schwab was no ordinary laborer. He was ambitious, charismatic, and possessed a brilliant mind for the business of steel. He rose through the ranks with astonishing speed, becoming president of Carnegie Steel at the age of 35. In 1901, he helped orchestrate the deal of the century, the merger that created U.S. Steel, the world's first billion-dollar corporation. But Schwab's restless ambition and his penchant for high living clashed with the buttoned-down culture of U.S. Steel. In 1904, he took a gamble. He left the security of the world's largest corporation and took control of a small, struggling company in eastern Pennsylvania, Bethlehem Steel. At the time, Bethlehem was a minor player, a producer of rails and structural steel. But Schwab had a vision. He believed the future of steel was not in rails, but in specialized, high-value products, particularly armaments. He traveled to Europe and visited the great armaments works of Krupp, Vickers, and Schneider. He saw firsthand the advanced technologies they were using to produce guns and armor plate. He returned to America convinced that Bethlehem could not only match the Europeans but surpass them. It was a hugely risky strategy. The U.S. government was a fickle customer, and the market for armaments was small in peacetime. To fund his vision, Schwab poured his own fortune into Bethlehem, borrowing heavily to finance the construction of new mills and the acquisition of the latest technology. He enticed the best and brightest engineers and metallurgists to come to Bethlehem, creating a culture of innovation and relentless experimentation. By the time war broke out in Europe in 1914, Bethlehem Steel, under Schwab's audacious leadership, was uniquely positioned. It was a company that had bet its future on the very products that the Allies, and soon the United States itself, would desperately need. The secret to superior armor plate lay in a complex, multi-stage process that transformed ordinary steel into a material capable of resisting the immense kinetic energy of an artillery shell. The process began with the steel itself. Bethlehem used a special nickel-chrome alloy, a formula developed through years of painstaking experimentation. The real magic, however, happened in the heat, treating and forging process. The first step was carburizing. The steel plate, sometimes over a foot thick, was placed in a massive furnace and baked for weeks in a carbon-rich material like charcoal or bone dust. This process, known as the Harvey process, caused carbon to slowly diffuse into the surface of the steel, creating a face of exceptionally hard, high-carbon steel. The back of the plate remained lower, carbon, tougher, and more ductile. This combination of a hard face and a tough back was the key to defeating armor-piercing shells. But there was a problem. The carburizing process was incredibly slow and expensive, and it didn't always produce a uniform case depth. To solve this, Bethlehem turned to a new technology, a modification of the Krupp process. Instead of just baking the steel, Bethlehem's engineers developed a method of spraying a hydrocarbon gas onto the surface of the hot steel, allowing for much faster and more precise control of the carbon diffusion. The next challenge was forging. To create armor plate of the required size and quality, you needed a forging press of immense power. Schwab had invested heavily in this area. Bethlehem's No. 2 press, a 14,000-ton behemoth, was the most powerful in the world. It could take a 150-ton ingot of steel and squeeze it like clay, shaping it into a massive plate of armor. The forging process itself was critical. It aligned the grain structure of the steel, eliminating internal voids and weaknesses. After forging, the plate was hardened. It was heated to a precise temperature, around 1,500 degrees Fahrenheit, and then rapidly quenched in a bath of oil or water. This rapid cooling locked the steel into a hard, brittle state. The final step was tempering. The hardened plate was reheated to a lower temperature, around 600 degrees Fahrenheit. This relieved the internal stresses created during quenching and restored some of the steel's ductility. The result was a piece of steel with a dual personality, a glass, hard face to shatter an incoming shell, and a tough, resilient back to absorb the impact and prevent spalling. It was a delicate balancing act of chemistry, temperature, and pressure, a process that took weeks to complete and required the skill of hundreds of workers. But the result was armor plate that was, quite simply, the best in the world. When the United States entered the war in April 1917, the demand for Bethlehem's armor plate exploded overnight. The company had the technology, but it faced a new and equally daunting challenge, scaling up production to meet the insatiable demands of a nation at war. The sleepy town of Bethlehem, Pennsylvania, was transformed into a 24-hour-day arsenal. The company embarked on a massive expansion, building new open hearth furnaces, new forging presses, and new machine shops. The workforce swelled from 24,000 in 1914 to over 100,000 by 1918. To find these workers, Bethlehem scoured the country. They recruited from the coal mines of Appalachia, the farms of the Midwest, and the immigrant communities of the East Coast. Women, who had been largely excluded from heavy industry, were hired in the thousands, working as crane operators, machine tool operators, and inspectors. The work was difficult and dangerous. The steel mill was a world of fire and noise, of molten metal and immense machinery. Accidents were common, and the hours were long. But the pay was good, and there was a palpable sense of patriotic duty. The workers of Bethlehem knew they were on the front lines of the industrial war. The numbers tell the story of this incredible industrial mobilization. In 1914, Bethlehem produced 1 million tons of steel. By 1918, that number had tripled to 3 million tons. Armor plate production, which had been a niche product before the war, became a torrent. The company produced armor for the Navy's new battleships, for the Army's tanks and artillery, and for the British and French armies. The scale of the operation was staggering. Bethlehem's gun shop No. 2, built in just 18 months, was the largest in the world, a single building a third of a mile long. The company even built its own railroad, the Philadelphia, Bethlehem, and New England, to move raw materials and finished products. It was a logistical miracle, a testament to the power of American industry when mobilized for a common purpose. Charles M. Schwab, the mastermind of this industrial symphony, was a ubiquitous presence in the mills, a cigar-chomping, back-slapping whirlwind of energy. He exhorted his workers, cajoled his managers, and charmed the government bureaucrats who controlled the purse strings. He was the P.T. Barnum of steel, and he was putting on the greatest show on earth. The ultimate test of Bethlehem's armor came not in a laboratory, but in the crucible of combat. In the North Sea, American battleships, clad in Bethlehem forged steel, joined the British Grand Fleet in the blockade of Germany. On several occasions, these ships came under fire from German U-boats and, in one instance, a German surface raider. The armor held. The German shells, which had proven so effective against British battlecruisers at the Battle of Jutland, were defeated by the superior quality of the American-made plate. But the most dramatic validation of Bethlehem's technology came on the Western Front. In the final months of the war, the American Expeditionary Forces began to deploy their own tanks, the M1917 and the British-designed Mark V. The first batches of these tanks were armored with British or French plate. But as the war progressed, an increasing number were built with Bethlehem Steel. The difference was immediately apparent. The American-made armor was more resistant to German anti-tank rifles and artillery fire. In the Meuse Argonne Offensive, the final and largest battle of the war for the AEF, American tanks played a crucial role in breaking through the German defenses. The after-action reports are filled with accounts of tanks surviving multiple hits from German guns, their crews saved by the strength of their armor. One report from a tank commander in the 344th Tank Battalion describes his Mark V tank taking a direct hit from a German 77 field gun. The shell, he wrote, struck the left front sponson door, making a dent about 2 inches deep. The door was bulged inward, but not penetrated. None of the crew was injured. For the crew of that tank, the abstract science of metallurgy had become a very real and very personal matter of life and death. The enemy, too, recognized the superiority of American armor. Captured German intelligence reports from late 1918 note the difficulty of knocking out the newer American tanks. Post-war analysis by German ordnance experts confirmed that the American nickel chrome plate was, on average, 10–15% more effective than their own armor on a thickness-for-thickness basis. The lives saved by this technological edge are impossible to calculate, but they are undoubtedly in the thousands. for the soldiers and sailors who went into battle protected by Bethlehem Steel. It was the difference between coming home and becoming a statistic. By the time the armistice was signed on November 11, 1918, Bethlehem Steel had produced a staggering 60% of the finished guns and 40% of the armor plate used by the American military in the war. The company's total steel production during the war years exceeded that of the entire Austro-Hungarian Empire. The strategic impact of this industrial achievement was immense. It allowed the United States to build a modern navy and to equip its army with the tools of 20th century warfare. It gave American and Allied forces a critical technological edge on the battlefield, saving countless lives and hastening the end of the war. After the war, Bethlehem's dominance in the armor plate market continued. The company became the primary supplier of armor for the U.S. Navy's post-war shipbuilding program, including the iconic battleships of the Second World War. The USS Missouri, the ship on which the Japanese surrender was signed in 1945, was protected by a belt of Bethlehem armor over a foot thick. The technology pioneered by Bethlehem in the First World War became the foundation for the development of even more advanced armor steels in the decades that followed. The principles of alloy design, heat treatment, and forging developed in the mills of Bethlehem were adapted and refined to create the armor that protected the tanks of the Korean War, the armored personnel carriers of the Vietnam War, and the fighting vehicles of today. The company itself, after a long and storied history, fell victim to the decline of the American steel industry in the late 20th century. The last heat at the Bethlehem plant was tapped in 1995, and the company declared bankruptcy in 2001. The massive mills that had once been the arsenal of democracy were torn down, replaced by a casino and a shopping mall. But the legacy of Bethlehem Steel and its visionary leader Charles M. Schwab lives on. It is a legacy written in steel, a story of innovation, ambition, and the enduring power of American industry. In the years after the war, the young lieutenant from Ohio, whose M1917 tank was destroyed in the Meuse, Argonne, was posthumously awarded the Distinguished Service Cross. His story, and the stories of countless others like him, is a stark reminder of the price of unpreparedness. The failure to provide American soldiers and sailors with the best available technology was a national scandal, a lesson paid for in blood. The story of Bethlehem Steel is the other side of that coin. It is a story of how a single company, driven by the vision of one man, rose to meet a national crisis. It is a story of how science, engineering, and sheer industrial muscle can change the course of history. There is a final, poignant irony to this story. The technology that made Bethlehem's armor so effective, the nickel-chrome-steel alloy, was not an American invention. It was based on German and French patents. Bethlehem's genius was not in the initial discovery, but in the relentless and quintessentially American process of refinement, innovation, and mass production. Today, the principles of heat-treated alloy steel are ubiquitous. They are in the landing gear of the airliner you fly in, the engine of the car you drive, the surgical tools in the operating room. Every time you use a product that requires high-strength, resilient steel, you are using a technology that was perfected in the fiery furnaces of Bethlehem, a technology that saved thousands of lives and helped win a world war. It is a silent testament to a time when American industry, faced with an existential threat, forged the tools of victory.